Thank you very much, and I'd like to thank Professor Hua for organizing such a wonderful conference and for such an August event. And also, I'd like to relate a little background. I got my degree in 1964, and I went to the Institute for Advanced Study for my postdoc training. And at the time, Julian Schwinger was my advisor, and he was doing all kinds of commutators of non-abelian gauge fields and also gravity to try to check the consistency of such a theory. And so I went to Professor Yang and asked him, what do you think of this? He said, well, what you really should really concentrate is the unitarity of the equations rather than such an abstract commutator and the algebraic aspect of the theory. But at the time, the currency was current algebra, so I didn't pursue that much. And so after that, for many years, every now and then I would do some strong interaction correction to the electroweak interactions. And so today I want to talk about something that I did with a postdoc and also who's now an associate professor at Virginia, Deanna Varman, and also with the CS Lab. And now the title should have a plural, should be equations rather than equation. If it's an equation, then the problem becomes extremely trivial. So what's the problem? The problem is the following. Wait a minute. Okay. We have two beautiful theories, and one is the general relativity and one is Yang-Mills theory. On the other hand, if you try to calculate the amplitudes by using covariant method, it's a horror. And so in the past 15 years or so, people have made advances and by using some rather ingenious method. And now, but in the past, about 5 years ago, there was another proposal by three people. That's Katsaso, Li, and Yuan. And they said that if you insist on having what's called the Mobius invariance, you can just write down a very simple formula, and that would produce all the amplitudes. Okay? And so now I would like to go through this development in the sort of Feynman way first, and then I will talk about how we can apply this kind of a method to go to consider the proposal by CHL. Yuan actually is Yuan, and yeah. Okay, so in so doing, I also would develop my language to do the problem. So first of all, the advance in the past almost 15 years now would be the spin and twister technique, okay, to simplify calculation, and also to use unitarity and also analyticity to try to get recursion relations, okay? Because you spend so much effort to perform a calculation, and then when you try to do another number of particles in the process, you dump away all your former effort. And then this particular way will allow you to somehow use what you did before and try to get onto more particles. And I would not be able to talk about that much about the color kinematics duality and also double copy connection. But the double copy connection would be a proposal by these three authors, how they would do it. Okay, so I'll come back to this later on. Okay, that will be the second part of my talk. So the spinner technique, as we all know, is that rather than just writing down your polarization vectors, in fact, you solve the Weyl equation, and then you write your polarization tensor as this. Okay, so what you find is that you have some reference vectors for a particular momentum of your gluon or photon or whatever. And by choosing this particular reference vector very cleverly, you can reduce your calculation by 10 times, okay? And if not more. And Professor T.D. Wu made great contribution in this direction. So let's say that each gluon can have its own reference vector, and you know how to choose vectors, and then you can just simplify your calculation. Okay, the next point that I'll come to is unitarity, and also how to do cuts in order to do recursion. And what happened is that in the past, when people talk about unitarity, they talk about something plus its complex conjugate and equals something. But when you try to calculate an amplitude, you're really not that much interested in something plus complex conjugate, because you end up with an optical theorem, and that's not what you want. Instead, there is such a thing which is called the largest time equation. So suppose I have, suppose I have the product of a two photon propagator, then I can write it as just one propagator plus the cut propagator, except that you find that in here the times x1, x2, and x2, x3. Now the theta function is from x1 to x3, okay? And so that's why it's called the largest time equation. And if you now properly or cleverly write down representation for this step function, okay, and continue in momentum space to some direction, and you find that this particular equation here will allow you to generate the 5-point functions into the product of 4-point function and 3-point function. And so now Witten and his 3 students did not do that way. Instead, they said that suppose I want to make a cut in such a way that I maintain the massless nature of the incoming, outgoing particles, okay? And the way they did it was to take one of the momenta, and just make a shift on either its pointed solution or the bracket solution, okay? And you do the annulment with respect to the bracket rather than the pointed. So these are the 2 different kinds of solutions. So actually the 4 different kinds of solutions of the dry equations, okay? And now if you do that, what happens is that we know that the particle momentum can be written as the product of the pointed and also the square, whatever you call it. And but because it's an outer product, you find that automatically p squared, which is the determinant of this guy here, is going to be 0. Okay, so you complexify your momentum, and at the same time you keep the massless nature of the particle, and that's what you want, because when you try to calculate amplitudes recursively, you do not want to have some crazy amplitudes which are not massless amplitudes to begin with. Okay. Okay, so they say that now let's take an amplitude and continue the particular amplitude in the way that I talked about a while ago by introducing a complex variable z. When z equals 0, then of course you recover the original amplitude. But if you assume that the z going to infinity is equal to 0, at least fast enough, okay? And then you find that you do this particular integral here, then you, of course, get just 0. Because remember now, I'm talking about 3 amplitudes. And so the function is a rational function of z. There are no cuts or anything like that to begin with, okay? And so then you find that this particular thing here is going to be equal to original amplitude and then plus a bunch of other poles in AZ. And these other bunch of poles correspond to the product of the lower amplitudes and divided thus by wait a minute, where did I go to? Okay, so it's going to be equal to the product of some lower number of particle amplitudes. Okay. Now there are two things that, of course, you have to justify. Okay? First of all, how do you know that your amplitude goes to 0 when z goes to infinity? Okay. And secondly, there are two parts in a Feynman diagram. One is the numerator and one is the denominator. Now you're telling me that you know how to factorize your denominator, but how do I know that I know how to factorize a numerator in such a way that I can identify, in fact, that I do get an amplitude? Okay. So the way that one can justify this particular claim is that you choose a gauge, and which is a light gauge. Okay? And so say you take the two vectors or spinors, plus or minus, you form the product of 4 of these guys. Okay. And then you say that I am going to insist that the component of my vector field in this particular combination is equal to 0. Okay? So this is what's known as the space cone gauge. Okay? Now, once you do that, you find that, so I have a notation that for 4 components, I plus, minus, and also bar and unbar components. Okay. And so insist the unbar component is equal to 0, then the bar component becomes a dependent variable, and you quantize your system, you find that that's what you get. Okay? Now, there are several things that are very interesting about this particular Lagrangian. First of all, you get now just only 2 fields. One corresponds to helicity plus and one corresponds to helicity minus. Okay? And also you find that in this particular Hamiltonian here, except for the free part, except for this part here, there is no bar dependence at all. Okay? Particularly the interaction part has no bar dependence, only depends on plus and also the unbar. And so also what you see is that there is no G mu nu or things like that to contract one vertex to another. Okay? So in other words, if you do a Fourier transform of the interaction is localized at the vertex. And you don't have to, the reason that it's so difficult to do a Feynman diagram calculation in the covariant gauge is that you find that G mu nu propagates all over the place. You get thousands of terms, but here you get by a factor of at least about 50. Okay? So now we are dealing with the theory of a 2 charge scalar coupled to each other. And the polarization vector basically would be coming out from the wave function of the scalar fields. Okay? So then you look at it again, you find that now you have a situation such that if I look at the momentum space, okay, I had 3 blocks of terms. One block is the external wave function, and that's trivial. Okay? It just separates itself out. And then there's another block that corresponds to the plus minus component. And then another block, which would be the unbar components of the momentum. Okay? And so because of the fact that there's no dependence on the bar component, if I do another continuation of my momenta in the bar direction, then all the z dependence would just come from the propagator. Okay? And if I can somehow find a proper choice of my reference vectors to get rid of the last term, okay, then I get enough suppressions all the time to justify that z going to infinity is satisfied. And at the same time, I find that if I do this continuation, I do not have to change my numerators at all. The numerator just is immune to this particular thing here. And that makes sort of reconstructing the amplitudes a lot easier, right? Because you know what they are. And okay. So I just said that. So now this part I will not have time to talk about, but I just want to summarize. So since these are very important results, and suppose I take a 4-particle amplitude. Okay, I decompose them into the color coefficients and also the kinetic coefficients and also the denominators. Okay. Then I find that for the coupling, I have the product of the structural constants, and for the numerators, I have 4 particles. That's 3 different combinations, STU channel. Okay, and now what happened is that these 3 different products of color coefficients are not independent because of Jacobi identity. And if you perform a calculation, you find that in fact the numerators also satisfy the same Jacobi identity as the color coefficients. Okay? And therefore, you can write down the equation for your amplitude. And so the amplitude that I'm going to talk about now would be the so-called color amplitude to begin with. Okay? So because of this, there are only 2 numerators and also there are only 2 independent coefficients. I find that there will be only 2 independent amplitudes at most. Okay, so I write in this particular way, and then I write the numerator this way, and also I write a color coefficient this way. Okay, and if you do that, what happens is that you find that there's a matrix. This one, which connects the amplitudes, the color order amplitudes to the color order coefficients. Okay. Now, if you stare at it, you find that in fact that this particular matrix is singular in the sense that that there's got an eigenvector with eigenvalue 0. Okay. If you have a 0 eigenvalue, then you can shift your numerators by something that's proportional to this particular 0 eigenvector without affecting the amplitude. Okay? So your conclusion is that in fact you have just 1 independent amplitude rather than 2 independent amplitudes. Okay? So you can generalize this to any arbitrary n. Okay? So that thing that the Jacobi identity for the color coefficient and also for the numerator is called color kinematic duality. And so suppose you go to a higher number of particles and you calculate the same thing as I said a while ago, you find that first of all, the number of independent color coefficients for n particle is equal to n minus 2 factorial. Okay? And but with respect to the numerators, you find that you form the same kind of Jacobi as we have on the left-hand side, and that in fact is not equal to 0. Okay, you say, what's going on here, and doesn't this seem to work? But so you can make a shift of your numerator, okay? And suppose this thing is not equal to 0, you can in fact make a shift and you can calculate this particular equation. So there's an equation on the left-hand side which depends on something that doesn't satisfy Jacobi identity, and then right-hand side would tell you how much delta n you should get in order to make the thing work. Okay? Oh my God. Okay? So it turns out that after you've done that, you actually, because of color Jacobi identity, you just add a 0 effective Lagrangian into your theory, and you basically just shift your amplitudes all over the place. But the physical amplitude, which would be color multiplied by all these color order amplitudes, do not change at all. Okay? So now let me go on. Okay, then this the so-called double copy, it just says that you replace your color order coefficient by another set of numerators that's obtained from the gauge theory. Then you find that this particular amplitude would describe gravity for you. Okay. And, what CHY proposed was that, as you could see in my discussion, there are actually two very important components in the construction. One is the M matrix, okay? And on top of the M matrix, impose the N. And then you get all the dynamics that you need, okay? So one of the things that you want to construct first is the so-called M matrix, okay? The M matrix is basically just a matrix that the scaling amplitude corresponds to the scaling of a bunch of scalars with a structural constant as their coupling constants, okay? So and then they said if you want to get the amplitudes, first you construct this guy, okay? And the way you get it is that you solve for a set of equations. And that set of equations is composed of the Sij, which will be the invariant product of the two physical particles with momentum I and j, and then divided by a whole bunch of complex numbers. And these complex numbers are called sigma ij, okay? And so you solve these equations, you get your solution as the sigma ij as a function of a kinematic invariance, okay? And then you stick your solution into a magic formula, then you get all the amplitudes you want. Now the problem is the following, that there is this fundamental theorem algebra. If you have a set of equations, okay, and of high order, then you get all kinds of square roots and whatnot for your invariance. And we know that we're talking about a tree amplitude, and there is no square root of anything at all. Okay, it has to and therefore the thing is you want to avoid, okay, all these kinematic the solution the roots of these equations, okay, and the way to do it is to go to complex plane to try to avoid having to solve for the equation having some funny roots. Okay. So you find that what happened is that these things here, if they are massless, then you find that they, under this Mobius transformation, they transform like this, okay? So now, suppose you form three equations, okay? So we weighted these f by the complex number that I talked about. You find that you get three equations, and if all the particles are massless, you find that you have three conditions on these equations, okay? In other words, you find that only n minus 3 of these equations are independent, and you can just use these rather than the whole set to find a solution, okay? And let me just skip this, okay? And so they say that now all you do is to take this particular integral and you integrate over the simultaneous poles of the fi over here, and then you should get the scattering amplitudes, okay? And so this particular equation here is invariant under the Mobius transformation. And so also all the dynamics in the particular theory eventually would come from these particular factors here, which are called the sigmas. Okay? And so sigmas would be defined as a product. You start from 1 and you end up with n. Okay? So for each n particle process, you find that there are n minus 1 number of sigma ij in there. And these sigma ij's, later on, when I do a plot, they would correspond to some lengths, whereas the i's would correspond to vertices of a particular plot. Okay. And so what do we do? And because of the and you can show that in fact the solution, the result that you get from this integration is independent of the some 3 equations that you don't want to include, and those what I call the PQR. And so, for example, suppose I want to do a 5-particle calculation. What I do? I am supposed to calculate the residues due to the vanishing of F3 and F4. Okay? And because of the fact that this particular integrand is a rational function of z, I find that I can use the so-called global residue theorem, and instead of calculating the residue of F3 and F4 simultaneously, when I integrate over d sigma 4, I would just calculate the residues due to having F4 finite and then try to get the residues due to all the other variables. Okay? And so this way, as you can see, that I don't have to solve a quadratic equation anymore. I mean, I just have a linear equation to solve and look for the pole, and then I would get my 5-particle amplitude immediately. So the philosophy now is to do it over and over again by using this global residue theorem, so that you don't have to solve for these simultaneous equations. Okay, and so in view of time, okay, let me talk about something that's very important. Suppose I just look at the 5-particle thing again. I'm supposed to look for, say, F3 equals 0. F4 is now not equal to 0 anymore, okay? And I'm supposed to take one of variable to go to 0 with it. Suppose that particular variable that I want to take with it is going to 0 is, say, sigma 3, 1, okay? And you find that you get this particular equation which has to vanish. Now, the only way that this particular equation can vanish when z goes to 0 is that you have to have some special way to scale your sigma 3, 4. Okay? And so by introducing a particular scale, you find that you force the other variables to scale also. And so you can now then divide the variables that you want to integrate into a set that would have to be to make the F4 non-vanishing, and the other guys to be just equal to some finite number. And in so doing, you find that you get factorization. Okay. So the philosophy of doing, I'm just going to describe what's going on with respect to gauge theory now. The way that you do a gauge theory is basically just the same. And by using this kind of a scaling, you want to be able to somehow factorize your integrand into different pieces. And now I have already said that the numerators are simple because they factor into 3 groups. And the plus components would correspond to having 2 negative helicity particles coming in. And then the plus or the minus thing would correspond to having 2 minus helicity particles coming in with another negative helicity particle. And you just reconstruct, the thing after you factorize the thing, and then you will be able to reconstruct your amplitude. And so this process is still being continued. We've been able to do it to up to 5 particles at the moment. And the thing is to look for some general pattern. And it turns out that by looking at the structure of the sigmas as a trajectory with some of the you have this a cycle, right? Sigma 1, I, sigma 1, and I1, I2, I2, I3. So you have a thing that comes back and so by looking at the overlap of these two cycles, you'll be able to tell exactly where you're going to have a pole. In other words, where you're going to have a 1 over Sij pole. Okay, and this way you would be able to get the result rather easily. For 5 particles and things like that, it's easy to do, and it's very fast. Okay, but when you try to see whether there's a general pattern for n particle, the problem is that these loops might go into themselves again. I mean, they may actually have a closed loop inside a loop, and then you're in trouble. You say, gee, I don't know what's going on here, and we have to untangle such trajectory to come up with something that we can identify as where we should be making the cuts. Thank you very much.